This is the first section of the elastic collisions in 2 dimensions, and this is an oblique impact with a fixed surface. Now we've done normal impacts with a fixed surface. That means that an object has hit a fixed surface at a perpendicular angle. So we've done things like this, where this would be u and this would be v, and we'd have like the coefficient of restitution, which is v over u. The only difference now is that we have things impact at an angle. So like anything in mechanics where we have things at an angle, we need to work out what the separate components are. So these green arrows here represent the components of the forces or components of the speeds which are perpendicular to the fixed surface. So these green arrows here, they would be perpendicular, and if I do these blue arrows here, these blue arrows would be the component of the speeds which are parallel to the fixed surface. So we're going to be looking at things which are perpendicular and parallel. So let's just write on what these components are. So this would be u sine alpha, this will be u cos alpha. Moving across, we would have v cos beta, and right on the right hand side we'd have v sine beta. Now what's special about this is that if we look at the components which are parallel to the fixed surface or the fixed plane, those velocities don't change. Okay, so they're constant. So velocity constant in this direction. So that will give us this equation, which is u cos alpha equals v cos beta. Yeah, so parallel to the fixed surface, the velocity doesn't change, but it does change perpendicular to the first fixed surface. So perpendicular to the fixed surface, there will be a change in the velocities, and that will be connected to the coefficient of restitution. So the coefficient of restitution E will equal like the speed of rebound, which is v sine beta, over the speed of approach, which is u sine alpha. So these are two equations which we can use. So in one direction, the parallel direction, the velocities are parallel. In the perpendicular direction, there is a slowing down of velocity, and that will be given by the coefficient of restitution. That will give us the link between the two. And also in these questions, we may be asked to find the angle of deflection. Okay, and the angle of deflection is the angle alpha plus the angle beta. It's almost like the total angle which the sphere or particle or object has moved through. It's moved through a total of alpha plus beta degrees. So that's what we call the angle of deflection. Right, so we have a smooth sphere moving on a smooth horizontal plane, so there's no friction at all, and with speed u, and then it collides with the smooth fixed vertical wall. Everything is smooth. At the instant of collision, the direction of motion at S makes an angle of 60 degrees with the wall. The coefficient of friction between S and the wall is a quarter. Find the speed of s immediately after the collision. Right, so this is a vertical wall, so let's draw it as such, like this, and s collides with the wall, so it's moving this way. It makes an angle of 60 degrees, and it's moving with speed u, then it bounces off the wall like this. We'll call the speed that it leaves the wall, we'll call that v, so that's something we're going to need to find. And this angle here, we'll call that angle beta, so we may need to find that as well. So I think part A is finding v, and part B is finding beta, and we're told that the coefficient of restitution between the particle, the sphere on the wall, is 1/4. So let's start with part A. So the first thing we're going to do is write down the components. So these components here we know are equal. Yeah, so this velocity that's parallel to the wall or the fixed surface doesn't change. Now this one at the top here, it will be u cos 60. Now cos 60 is actual, we'll work that in a minute. And this one here is going to be v cos beta. Now we know they're equal, so first equation I'll have is u cos 60 equals v cos beta. So yeah, a minute ago I was going to work out cos 60. That's a half. So I will have a half u equals v cos beta. Okay, so I'm going to need another equation because beta is unknown, and because I've been given the that approach speed as u, I'm not going to be finding u. My answer is going to be in terms of u. So the perpendicular velocities are going to be these here. Yeah. So this one up here is going to be u sine 60, and this one will be v sine beta. So we have the coefficient of restitution, which is 1/4, which means that 1/4 is equal to the speed of rebound, or the perpendicular speed of rebound, which is v sine beta, divided by the perpendicular speed of approach, which is u sine 60. So let's just work out what sine 60 is, see if we can simplify it a bit. So sine 60, √3/2. So I'll have 1/4 equals v sine beta over √3/2 u. Now what I want to do to find v is I actually need to eliminate beta from the equations, and actually the best way to do that is to use sine squared plus cos squared, and in this case it'll be sine squared beta plus cos squared beta is 1. That's the best way to do it, because if I try doing sine over cos to get tan, I'll actually end up doing v divided by v and actually eliminating v as well, which is what I don't want. So using sine squared beta plus cos squared beta, so the first equation I've got is that v cos beta equals u/2, and then the second equation I will have, if I multiply both sides by this, I'll have √3/8u. Okay, so let's write that down. So that'll be √3u/8 equals v sine beta. Okay. So now I will square both of those. So v sine beta all squared plus v cos beta all squared, so that's like my sine squared plus cos squared, is going to equal this root 3u over 8 squared plus u over 2 all squared. Now the bits in the brackets here, I'll get v squared sine squared, v squared sine squared, so I'm going to take the v squared out, so I'll have v squared, and then I'll basically have sine squared beta plus cos squared beta, which I know is 1, and that equals what I've got on the other side. Now if I square that, I will get 3u squared over 8 plus u squared over 4. Sorry, not over 8, over 64. 8 squared is 64. Should know that by now. Yeah, so sorry about that, yeah. Then this part here just becomes 1. So next step, I will have v squared equals 3u squared over 64 plus u squared over 4. If I make the denominators the same, that means timesing the second fraction, the top and the bottom, by 16. I will have 16u squared over 64. So that gives me v squared equals 19u squared over 64. Square root both sides, and I will have v equals root 19u over 8. So that is my value of v. So that's the speed of s immediately after the collision. Let's just tidy it up. That's a 19 there. So root 19, like that. Part B, what we need to do, it says find the angle of deflection of S. Now remember, the angle of deflection is alpha plus beta. So it's not just beta, it's alpha plus beta. So it's going to be 60 plus whatever beta is. So now we're going to work out beta. So I'm going to take this first equation here, and I'm going to substitute v for this root 19u over 8. So if I do that over here, so I will get half u, or u over 2, equals v cos beta. Now v is this, root 19u over 8 cos beta. Now u cancels out from both sides, and then if I rearrange it, so I get cos beta as the subject, so times both sides by 8 over root 19, what I will get is 8 over 2 root 19. Okay, so now it's just a matter of doing the cos inverse. Yeah, so cos inverse of that, 8 over 2 root 19 will give us beta. So we'll do that now. Cos inverse of 8 over 2 root 19, and we get 23.413 blah, blah, blah degrees. So the angle of deflection, so we'll write it over here, is going to be 60 plus that. So we get 83.4 degrees to one decimal place, 3 significant figures. So 83.4 degrees. So don't forget, you need to add alpha and beta to get the angle of deflection. It's not just the value of beta. So let me just highlight these answers. So this was part A, and here's our answer to part B. Okay, a small smooth ball is falling vertically. Okay, so there may be some soother involved in this. The ball strikes a smooth plane which is inclined at an angle of alpha to the horizontal, where tan alpha equals 1/2. Immediately before striking the plane, the ball has a speed 5 meters per second. The coefficient of restitution between the ball and the plane is 1/2. Find the speed of the ball immediately after the impact. So what this looks like is the ball is falling onto a smooth plane which is raised up at an angle like this, yeah, and that angle is alpha, and we know that tan alpha equals 1/2. So as soon as I see those types of things, straight away I'm drawing my triangle, I'm putting alpha in, I'm putting the opposite and the adjacent in, and I'm working out the hypotenuse, which would be √5, if I'm correct. 2 squared plus 1 squared, yeah, √5. So then I can write down straight away sine alpha equals 1 over √5, and cos alpha is going to be 2 over √5. So I will do those things straight away. Now the ball is falling down like this. Yeah, so that's where the ball comes from. So it drops down like that. And it has a speed of 5 just before it strikes, and then it's going to bounce off at some angle. I've put horizontal, but don't go by what my diagram looks like. We actually need to put on here like alpha and beta. Okay, so this is alpha here, and maybe I'm going to change my that just in case you think it's horizontal. I'm going to do it like this to avoid any confusion, and that angle there would be beta. Now I've just realised it's probably not a good idea to use alpha here, seeing as that angle of incline is given as alpha. So let me call that theta instead. Now just like before, I need to work out these components here. So this component here, this component here, and this component here. And we're trying to find the speed of the ball immediately after impact, so let's call that u. So what we have over this side here is going to be u sine beta. This bit here is going to be u cos beta. Now we can show, using a little bit of angle rules, that it's going to be this angle at the top here is actually going to be alpha. This angle here is going to be alpha. If you think about it, we've got this right angle triangle here and this line going straight down. That's going to be a 90-degree angle there. Then if I were to draw like a line that went straight across like this, yeah, we have a Z angle here, yeah, so this angle would be alpha, yeah, Z angle. So if this angle is alpha and this is 90 here between the green line and the red line there, now this is a straight line, so we know all the angles add up to 180. So this angle is alpha, this is 90, this angle here must be 90 minus alpha, which means this angle here must be alpha. So you'll find this angle here will be the same as alpha. You don't need to prove it, but if you can sort of remember, when you've got this type of situation, this angle at the top will always be the same as the angle of incline. It will sort of make things a little bit easier for you. So because that angle at the top there is alpha, and let's mark that in. So this angle is alpha. That means that this sort of component of the velocity or the speed is going to be 5 cos alpha. So I'll just put that in, 5 cos alpha. And the bit at the bottom, this will be 5 sine alpha. So 5 sine alpha. Okay, now we know cos alpha is 2 over root 5. So this is basically 10 over root 5. Yeah, because it's just going to be 5 times 2 over root 5. And the one at the bottom here, this will be 5 times 1 over root 5. So this will just be 5 over root 5. So we have the exact values of those components. So let's start by looking at the velocities which are parallel to the slope. So we know that these are going to be equal. So we've got 5 sine alpha equals u cos beta, u cos beta. Now 5 sine alpha was just 5 over root 5. So we have u cos beta equals 5 over root 5. Now what we're trying to find, the speed of the ball. So we're actually trying to find u. So we're going to need another equation. So now we're going to be looking at what's going on perpendicular to the slope. Perpendicular to the slope. So this is where we use the coefficient of friction. Coefficient of friction is, in this case, a half. The speed of rebound in this case is u sine beta, divided by the speed of approach, which is 5 cos alpha. That equals a half. Now 5 cos alpha we worked out to be 10 over root 5. So we'll have u sine beta over 10 over root 5 equals a half. Now, since this question is saying find the speed of the ball after the impact, what we need to do is we need to know what this part is and this part here, and do Pythagoras on it. So we want to know what's this component, so that we can find this part here, which means doing Pythagoras on this and this. So I'm going to draw a little diagram over here at the side to sort of try and explain what it is we're trying to find. So we're trying to find this that we've called u, and we have these two components. This bit here is the u cos beta, and this part here is the u sine beta. Now actually we've got u cos beta, haven't we? We've got u cos beta up here. So we know the length of this side down here is 5 over root 5. So I'll just put that in. So this is equal to 5 over root 5. So we've got half our Pythagoras. Now I'm going to use this equation here to work out what u sine beta is. So actually in this question I don't need to work out beta, I just need to know what are these lengths, and I've got enough information to find it. I've got this one here, just need to find this one here. So basically if I cross multiply and divide both sides by 2, that will give me u, I keep wanting to put mu, u sine beta equals 10 over 2 root 5, and if we simplify that, that simplifies to root 5. And actually this 5 over root 5, I think that simplifies to root 5 as well, by rationalising the denominator. So we've got this length is root 5. So the speed, which we've called u, is equal to Pythagoras done on these two components. So the square root of 5 squared plus the square root of 5 squared, and that will give us basically root of 5 plus 5, so root 10, which we can leave as that if we want, meters per second, or change it to 3 significant figures. But there, that will be our final answer for this question. So notice we didn't need to work out the actual angle that it sort of rebounds at. We just wanted to know what the size of those two components were, so we could then use Pythagoras on it. Okay, so we have a small smooth ball of mass 2 kg moving in the xy plane. It collides with a smooth fixed vertical wall which contains the y-axis. So we've got like a question where we've got like the x and the y-axis like this, and the y-axis is where the wall is basically. So let's say that our wall is like this. The velocity of the ball before the impact is -6 minus 4. So let's try and draw this so it's sort of to scale. So -6 minus 4 means it's moving actually down and this way, like this. Okay, so that velocity is -6I minus 4J meters per second just before the impact, and then it rebounds off like this. The coefficient of restitution is 1/3, and we want to find the velocity of the ball after impact. So the velocity of the ball after impact is going to be AI plus BJ, and we need to work out what A and B are. So let's draw on the components. So we've got this component of the speed as it approaches the wall, and we've got this component here, and then we've got these two components as it rebounds from the wall. Now as it goes towards the wall, the I part is 6, so this is 6 here. This part here will be 4, so -4, which also means that this will be -4 as well. So let's put the negatives on as well. So the bit that's missing, the bit that we need to work out, is this. Now this is actually the AU part of my vector because it's the one that goes in the x direction. Yeah. So first thing is that if I look in the components which are parallel to the wall, they remain unchanged. So the -4 before is going to be the -4 afterwards. So the J part stays as -4. So in my working here, B is going to be -4. Perpendicular to the wall, So it might be helpful actually for me to put here that parallel to the wall is actually the J direction. Yeah, because that's the one that's going up and down. Perpendicular to the wall, that's the one in the I direction. So that might be helpful to do that. Yeah, so perpendicular to the wall, that's the I component of the vector. I know that the coefficient of restitution, which is 1/3, will equal the component of rebound, which is the bit I'm trying to find, A, divided by the component of approach, which is 6. So from that I will get 3A equals 6, so that means that A is 2. So my final answer, my I part is A, so 2I, and my J part is B, so 2I minus 4J meters per second. Okay, now part B is asking for the kinetic energy lost as a result of the impact. So hopefully we'll remember that the loss of kinetic energy is the kinetic energy after the collision minus the kinetic energy before the collision, which means we need to work out U and V. So let's work those out. So U, now remember we need the speed, not the velocity, so that means I need to use Pythagoras. So before the collision U, I've got 6, negative 6 and negative 4, so that's going to be Pythagoras on negative 6 and negative 4, so that'd be the square root of 36 plus 16, so root 52. Okay, so that's my value of U. And V, so V is what I worked out in my second bit, so that's going to be the square root of 2 squared plus negative 4 squared, so that's going to be square root of 4 plus 16, which is root 20. So our loss of KE is going to be half m, now we've got the mass is 2, times by v squared, so that's going to be root 20 squared, so basically it's 20, minus half m times by root 52 squared, which is just going to be 52. So we'll work that out. So basically the first bit is 20, then the second part is just going to be 52, isn't it? Let me work it out. So that will give me minus 32, so it tells me it's a loss. So that because I know it's a loss, I could say it's a gain of negative 32, but seeing as we already know it's a loss, we would say that it's 32 joules. Now what you could do is actually work out the two amounts of kinetic energy separately, and then just do the biggest one minus the smallest one, because we know it's a loss. So I'm expecting a negative in this case, because there's more kinetic energy before than there was afterwards. Okay, now part C, it says the angle of deflection. Now the angle of deflection is going to be this angle plus this angle here. Okay, so let me just mark those in, maybe with a highlighter. So this angle here plus this angle here, that's going to give me the angle of deflection. So the one at the top, that's going to be the tan inverse of 6 over 4, plus the one at the bottom, that's going to be the tan inverse of let's see, 2 over 4. Okay, so if I do that, let's just do that quickly, I will get an answer of 82.87. So 3 significant figures. and we'll go for 82.9 degrees. Now there is another way you can do it. You'll know from year 1 vectors that we can find the angle between two vectors. So I'll just put here alternative. So if I want to find the angle between two vectors, that'll be cos the cosine of the angle between them. Remember, is A dot B over length of A times by the length of B. Okay, so that gives me the angle between two vectors, and yeah, and that angle between them is actually the angle of deflection. So if I was going to do it this way, the cosine of the angle between them, so I need to find the dot product between the two vectors. So maybe if I wrote the vectors like this, -6, -4, and what's the other one? 2, -4. So I want to find the dot product of those. So that would be 2 times by -6 plus -4 times by -4 divided by the length of those vectors. Now I've worked those out. Have I? Yeah, I worked them out. They were the bits that I used in the previous section. This is the length of the vectors here, so I've already worked them out. So I can just put root 52 times by root 20, and I'll get 1 over root 65, and if you do the cos inverse of that, you'll get the same answer as before. So that is an alternative way of working out this angle of deflection. Okay, you should now be able to do exercise 5A on pages 99 to 101. So just a quick recap. So we have our velocities that go like this. I'll do one over here like this. So we saw that these are the same. Yeah, they don't change. So parallel to the plane, they don't change. Perpendicular to the plane, these we can use our coefficient of restitution. So this would be u sine alpha, and this would be v sine beta. So v sine beta. So using the coefficient of restitution, we will have E equals v sine beta over u sine alpha. The angle of deflection is equal to angle alpha plus angle beta. And if the velocities are given as vectors, so if velocities are vectors, then the angle of deflection is, well, it'll be the cos inverse of this one. A dot B over length of A times by the length of B, where vectors A and B are the given velocities.